Okay, hello and welcome to the next lecture, part 2 of lecture 4. Okay, so we're making reasonable progress. What we're going to do this week, if you recall, last week we had generalized from nilpotent to solvable. And we'd recalled that we'd shown that for nilpotent Lie algebra, we had this very powerful theorem due to Engels first, well, two of them, Engels first and Engels second theorem. For solvable, the generalization of Engels' theorem to this solvable setting is called Lie's theorem. And let's just recall what that said. We stated this last week and we didn't prove it. What we're going to do in this lecture is to prove it. So let's just recall what it says, first of all. So that L be a solvable Lie algebra. Remember that we had a series of ideals constructed from the Lie bracket in a solvable Lie algebra, which eventually terminated. Okay, the derived series. Now, if we let L be a solvable Lie algebra, one for which this series terminates, eventually ends up at 0, over an algebraically closed field of characteristic 0. See here, we're limiting the fields that we're looking at. It's because results about Lie algebras, not all of them, but a lot of the more important ones, actually depend upon what field you're looking at, which I guess should not be such a surprise. Some things don't depend on the field, some things do. These theorems where we need to be careful, and we could actually weaken this a little bit. We're just going to state it in the setting of algebraically closed of characteristic 0. So again, think of the real or the complex numbers, and let rho V be a non-zero representation of Lie algebra representation. Then Lie's theorem says that in this setting, there exists a common eigenvector that should be eigenvector, not eigenvalue, eigenvector V, small v in big V, which is to say an eigenvector for rho of x for all x in L, which is to say the one-dimensional vector space spanned by this element, by this common eigenvector, is a subrepresentation. Okay, it's just an equivalent way of looking at it. So that's one consequence. Remember that we had for nilpotent, we had that there was going to be an eigenvector whose eigenvalue was 0. So it was going to be something that was killed by all of the elements of L. Here, when we generalize up to solvable, what happens is it's no longer, the eigenvalue is no longer 0. It's a general eigenvalue. Okay, that's where we see that's the generalizing process for this part of the result. There also exists a basis of the representation V such that looking at rho, remember you can consider any representation as a map from the Lie algebra into the linear operators on the vector space. If we have a choice, if we then have a choice of basis of the vector space, we can identify these linear operators with matrices. So we can think about the representation as mapping our Lie algebra into matrices. And there will exist, if it's solvable, there will exist a basis of V such that rho of x, the matrix, is upper triangular with respect to this basis for all x. Remember, in Engels' theorem, for nilpotent, what we had was strictly upper triangular. So that's how going to this more general setting of solvable weakens the result a little bit. Okay, in part 1, our eigenvalue went from being 0 to a general element of the field, a general scalar. And in part 2, we go from upper triangular to strictly upper triangular. Part 3, so there will exist a chain of sub-representations, just written as it is, starting off with 0 and working all the way up to V, such that the dimension of 1 quotiented by if we take 2 successive terms in this chain, in the sequence, then we quotient the larger space by the subspace. The subspace that we get is going to have dimension 1. Okay. Now remember, for Engels' theorem, what happened was that the Lie algebra actually moved you along the chain. So if you were in V1, yeah, it would move you successively up. We don't get that here. Okay, I should say sorry. It moved you down. That's what I'm trying to say. So if you were here, the Lie algebra, you're in V, which is to say V to the n. Then operating with that would move you into the subspace contained inside here, and into the subspace contained inside here, and so on and so on and so on. Okay, operating enough times by the Lie algebra would eventually bring you from here all the way down to 0. Okay. That's not the case here. These things are just sub-representations. However, this result, which we didn't actually state when we were looking at Engel's theorem, actually holds true for Engel's theorem as well. And you can see that from the way that we constructed it. You actually constructed from the basis. Okay, that's enough discussion of Lee's theorem. Let's prove it. That's going to be the subject of this lecture. So before we prove it, it's convenient or instructive, less confusing, to establish some preliminary lemmas first of all. And then using these preliminary lemmas, actually prove Lee's theorem. Okay, so it's the first one we start off with. And this is a very important tool that we'll be using again and again. So if we let L be a Lie algebra over a field K of characteristic 0, and we let I be an ideal. So here we're not asking for algebraically closed, we just need a characteristic 0. I is an ideal of the Lie algebra L, and V is a representation of L. Sorry, there should be a row here as well to be, sometimes we'd be a bit careless and omit the row, but it's a map from our Lie algebra into the linear operators on V. Then for any linear map, lambda, that goes from I to the field K, we introduce a space, okay, VW, V sub lambda, which is going to be all of those elements inside in V, such that, and here again, we're dropping the row, okay? So really, if we wanted to be completely precise, this is not X, it's row of X operating on V. But because it becomes a little bit troublesome or to keep on writing the row, it's sort of convention to drop it. So be careful about this. Though. Remember, it's really what's going on here is that it's row of X operating on V. But we want that when it operates, so we're identifying in this definition here, we're identifying those elements of V such that when we operate on them by X, the action of X is actually given by this linear map. This guy here, okay? So that's fine, we can define such a map, nothing going on there. It certainly makes sense, it's a vector space. If you add two elements together, they would still be in there. If you take on the element and you multiply by a scalar, it will certainly be in there. So it is definitely a subspace, a vector subspace. It's also a module over I. That's clear just by the definition of the thing. When you act on any element in W by X, you end up back inside in W because you're just multiplying by a scalar. And as we said, it's closed under scalar multiplication. The non-trivial part of the theorem is this, that in fact, even though W is defined in terms of I, it turns out that it's a submodule for the whole Lie algebra. Now, be careful, we're not asking that a general element of the Lie algebra L is going to act by some sort of scalar multiplication. This is not the case. Indeed, the condition here doesn't really make sense for a general X because lambda is a map from the ideal into K. Okay, so we don't really know anything. That the lemma is not telling us anything about the action of L on W. It's just saying that it's closed under the action, that it's a submodule. But this is a very powerful result, as we will see. So if W is 0, okay, which is to say we've made a bad choice of lambda, sorry, which is to say there were no elements satisfying this condition here, which is perfectly possible, then your space is going to be 0. But in the case it's 0, then it's clearly closed into the action of L, because L is going to operate on something which is 0 to give you 0. So then it holds trivially. Okay. So for the rest of the proof of the lemma, we're going to deal with the case where L is non-zero, because W is equal to 0 is taken care of. So How are we going to prove it? Well, we're going to prove this identity here. Okay. Or at least, yeah, this is what we're going to show. And why, if we're claiming that if we can show this, then the lemma would follow. And this is a one-line calculation that we'll just do. But basically what we're going to do now is convert the statement of, show that the statement of the proof is implied by this result here. Okay. So indeed, if that were the case, then for any x in L, any y in I, and v in W, we would have that x by y and v is equal to W, is equal to 0. Okay. So that's the assumption. The assumption is what we had up here, this condition here, just says that this identity holds for, it's notation for this identity holding for all elements of this form. Now, if that is the case, then let's look at y operating on xv. So x, remember, is in L. X is in the larger space. X is in the general element of the Lie algebra. Now, when we let it act on v, we want to show that this element lives inside in W. How do we show that it lives inside in W? Well, we test the defining condition for W. What's the defining condition for W? Well, it says that if you operate on it by y, you're going to get a scalar multiple. You're going to get lambda of y by this element. So if we could prove that that's true, then we know that xv is in there. We verify the condition. We verified for xv the defining condition of W. Okay, so let's write it as xv minus the commutator bracket. So remember now we've taken a representation. The representation goes into the general linear group of V. And it's a Lie algebra homomorphism, which means that it brings the Lie bracket of L to the commutator bracket of, to the commutator bracket inside the general linear group of V. And we know what that is. It's xy minus yx. So these two things here, this term here, and the second term will, the first term will cancel. So it leaves us just with the second term here. So this is good. But now we know that this guy is 0 by assumption, by assumption. So this goes away. So we're left now with x, y, v. But now this, of course, is associative, so we can bracket it as we want. So y, and now v is in W and y is in I. Y is in I. So that means by the definition of W that it's going to act as lambda by v. It's a scalar, so we can bring that up the front. And then we're left with lambda of y by xv. And that's precisely, and that is, there we're done. That's the condition for xv being inside in W verified. Hence we know that it's contained inside there. And this x was a general element, we know no assumptions on it. Therefore, we know that W is going to be a submodule of V. Okay. So that's what we have to do. We have to verify. We have to verify this condition here for every general triple of elements of this form. But we'd like to actually re-express this one more time. We're going to show that this. Okay, so here we've gone an intermediary point in notation between the previous general case and this. So yeah, well, I guess I don't need to explain it to you. You're smart guys, you can see it. The claim is that if this was 0, then it would imply this, okay? Why? Well, I is an ideal, so we know that xi is contained inside the ideal. Hence, we know that xi for any, or xy for any y and I, is going to act on W as lambda by this. So if this is, so then it means that this thing here is satisfied if and only if this is satisfied. Okay. So let's go on. Now, no surprise, given the amount of induction we've used before, that we're going to use an induction proof. There's a lot of induction in this course. It's a standard tool in proofs in Lie theory. So if we take 0, which is contained, so if we take a W contained in small w and big W, which is non-zero, okay, we're going to take a general element, and then we're going to produce a sequence of elements wk for k greater than I by acting on it continuously for some x. Okay, x is just a general choice. We're fixing a choice of element, but there's nothing special about it. It's a general element. And let us now show by induction how y operates on these elements here. So what we've done is, step back for a second, we've taken an element w, small w and big W. Y acts here through the scalar function lambda. But x is an element outside of the ideal. It's general element of x. So when you act on this w by x, or x to the k minus 1, we don't know that you land back in w. In fact, that's precisely what we're trying to prove. So that means then that if we take this wk is not necessarily contained inside in w. As I said, this is what we're trying to prove. So y will not necessarily act as lambda. Okay? This is not guaranteed. But what we're claiming is that we can show it acts as lambda on the first part, and then for all of the lower terms, it gives you a scalar multiplication. These AIs, they will depend upon, or they could possibly depend on y and k. Okay. I didn't include it in the notation just because it becomes a bit cumbersome, but they can depend on y and k. They're not independent. But the form that they take is not really important. What we're looking at in this formula here is we're actually saying, look, when we act by y, we end up getting a linear combination. We end up getting the wk back again acted on by lambda, plus terms where the I is less than, so it's further down the sequence of elements. Or more concisely, you don't get any term for wk plus 1, wk plus 2. It doesn't go up, it always goes down. That's the important part. Okay. So let's do it by induction. Let's try to prove this. Well, let's start off. If we have k is equal to 1, then we know that this is true. Because for the first series, it's w. W1 is w because this is x to the 0, so it's w. So it lives inside in w, so y is going to act on it by lambda. Okay, so easy. That's the first step done. Now let's assume that the identity holds for k and try to show that it holds for k plus 1. So let y operate on w to the k plus 1. Now, what's this? Well, we just write it out. This is what it is, because this is this by definition. Okay, so now we're going to take out the first, we're going to break this up into k minus 1, x to the k minus 1, and x. So now when I have xy, I'm going to break it up using the same trick I had before, using the commutator bracket. Okay, remember again, to repeat myself, we're in the general linear group on V, the general linear Lie algebra on V, and in there the commutator is, sorry, the Lie bracket is just the commutator. So this is true, and exactly the same reasons it was true before. Now we're going to take this and just group it back together. Okay, this is this by definition. That's what's going on in this step here, because this thing here stays exactly the same. Now, by assumption, and we're going to just distribute this over the bracket by multiplication. See that now when we bring this in, our y and our wk, our y is going to act on our wk. But how does that work? Well, we're down one term, so we can apply the inductive assumption, the inductive hypothesis. And we're going to get lambda y of k on the leading term. And then in the lower order terms, we're going to get some ai wi's. Okay? We don't care really what they are, just that the linear combination, we really just care about the fact that the limits of the summation terminate at k, everything is lower down. Okay, so this guy acting on this gives us this. Now, we move on to the next one. Well, this element here is contained inside in I, okay? And this wk it's lower down, so we can use the inductive hypothesis again. And here we're not going to write it in terms of lambda because we don't really care that much, and we'd have to write it in another term. So it's more compact to write it like this. But the point is that you're never going to get a k plus 1 here, because it's an element of the ideal acting on wk. Everything is going to be further down. Okay. Now we can group this and this together. Clearly, we just add up the constants, and then we introduce a new notation, this b sub I, because we're just taking this and this and subtracting. Except, of course, for the last term k, where it's just going to be ai prime. But as I said, we really don't care what the coefficients are. It's not important to us. So we're not going to go to the effort of writing it out explicitly. We can just introduce a new symbol for it. All right. But then suddenly we see what we arrive at. One thing. We then finally bring the x and let it act on the w. This is a scalar, so we can bring it out. We let the x act on the wk. What do we get? Wk plus 1 by definition. So now we've got this. What is it? It's precisely of the form we conjectured. Hence, if we've assumed it's true for k, then we know that it's true for k plus 1. Hence, by induction, we know that it holds for everything. So we now have this result, this identity in our pocket. Okay, so it's a long proof, but we're getting there, okay? So now with this identity in hand, we can consider the vector space U spanned by the elements wk. Now we note that since V is finite dimensional and U lives inside in V, this of course must also be finite dimensional. That means in particular that there's a maximal n such that this set is linearly independent. So there's a little bit of subtlety here that you should think about. But the point is, I guess you might ask yourself, well, could it happen that as we go up in the series from W1, W2, W3, that we could kind of skip one and remove it? I guess the point is that if at any point in your sequence of W1, 2, 3, 4, 5, your set becomes linearly dependent, then throwing this element away and continuing won't work. It will continue to be linear dependent. So once linear dependency stops, that's it. So there will exist a maximal n. Okay, so I don't know if my explanation of this is the best, but really you should just think about it yourself. It's basic linear algebra. There will exist a maximal n, such that this is linearly independent. And next we observe that by construction of U, it has to be closed under the action of x. That's clear. Okay. So move on. Now, taking these two pieces of information, taking the identity that we established by induction, and taking our new vector space U, together with its basis V, we see that Y in our ideal is going to act as an upper triangular matrix. Every Y in the ideal, or more precisely row of Y, is going to act on U as an upper triangular matrix with diagonal entries given by lambda of Y. Okay. This is the basis. That you should think about if it's not immediately clear. But I think it is. So if you remember, I was stressing the point that the formula that we had tells us that when we operate by Y, you end up getting terms that are lower down in the obvious ordering of the basis, 1, 2, 3, 4. You never get contributions that go up. And that, if you think about it in terms of a matrix, is precisely upper triangularity. Moreover, on the leading term, the WK, when we operated on this, what was the coefficient of this? The coefficient was lambda of Y. And that means that the diagonal entries are given by lambda of Y. Remember, the lambda Y, there was no dependence there on the K. So it operated on W1 as lambda Y, it operated on W2 of lambda y, W3 of lambda y, and so on and so on. So on the diagonal, it's always the same. And then you have all of these terms above. And just as I said before, we don't really care what form the terms upstairs have on the upper half of the matrix. That's not really important to us. What's important to us is that we have lambda y's on the diagonal and zeros below. That's why we didn't really take the time to write out what the ai minus ai prime and so on. We just denoted it as a b, because it's really a question of off diagonal, whether it's zero or non-zero. That's what concerns us. Okay, so anyway, from this we see that if we take the trace of rho of y, really, what are we going to get? We're going to get n lambda y. That's because if you, well, it's clear. Everything on the diagonal is just lambda y. The size of the matrix is n by n because it's an n-dimensional representation. Because our vector space U is n-dimensional, well, that's just really notation for the dimension. And this is what happens for every y. Okay. Now I is an ideal. So the previous identity can be applied to x by y. Okay. If we look at the matrix given by the Lie bracket of x and y, we operate on this. We take this image, the image of the Lie bracket of x and y on the row. Then it's an element of the ideal. So we know if we take the trace of that corresponding matrix, we're going to get this. Okay, it's going to be n times lambda of the element. So let's just go back 1 second. Here, y can be anything. So in particular, it can be this. Okay, I mean, we're using, hopefully it's not too confusing that we're using y in two different ways, but this is how it works. However, what happens over here? Well, remember, of course, that the trace, if you have the trace of xy, that's equal to the trace of yx. The trace doesn't see, for traces, matrices commute. Two matrices commute inside the trace. So that means the trace doesn't see the difference between x, y, and yx. So it's going to vanish on the commutator. And that means, of course, that this guy must be equal to 0. And now, so remember that we were assuming our field has got characteristic 0, and we haven't used it yet. Well, this is where we use it. Because now we want this to imply that lambda of the commutator bracket of x and y is 0. If we were in a non-characteristic field, we couldn't conclude this. A field with characteristic non-zero. If we're in some sort of finite field, then couldn't be sure of this. So this is precisely where we use the characteristic 0. But this is our assumption, therefore we can conclude it's 0. And finally, we've come to the point that, remember, we showed that if we knew that this identity or family of identities here was true if and only if this identity was true. But now we've proved this identity, therefore this is true. And finally, remember at the very start of the proof, we said that if this is true, then the lemma follows. Well, now we've shown this is true, therefore the lemma follows. Okay, so quite a long proof, but again, not really using anything except linear algebra. So because it was quite long, let's just go back and remind ourselves what it actually said. It just said that if we have an ideal, if we have a pair, I guess, consisting of an ideal and linear map from the ideal into the field K, then we can define a subspace W in this form. You just want it to be all the elements in V such that the elements of I act according to lambda. And then the claim is that this thing that we've constructed from I and lambda is in fact an L submodule. Okay, we went through a number of steps. First of all, showed that it was equivalent, that it was implied, by this identity here. Then we observed that that identity held if and only if this was true. for all x and y. And then we proved this using an inductive argument. Okay. Now, with this lemma in hand, we're now going to go back to Lee's theorem and prove it. This is the main ingredient that we need to be able to prove Lee's theorem. Okay, so let's have a look at that for 1 second. Remind yourselves of what's involved in Lee's theorem. Part 1, a common eigenvector. Part 2, a basis such that rho of x is always upper triangular. And finally, a chain of sub-representations such that one is codimension one or the other. Okay, so let's start with 1, a good place to start. So since L is solvable, we must have that the Lie bracket of L in itself is not equal to L. Okay, it can't give you back everything. Why? Well, if it did, then L1, which is the Lie bracket of L and L, would be equal to L, which would mean that L2 equal to L to the 1, L to the 1, would be equal to L by L, which would be equal to L. And so on. You see then if you repeat this and you look at 3, well, 3 is given by L2 and L2, and then that would be equal to L and L, which would be equal to L. So then we'd have L3 is L, and so on and so on and so on. So basically, taking this derived series, it's just continue. It would just be L for forever. So you would never get to 0. So then it couldn't be solvable. Hence, we have to conclude that it's going to be solvable only if this commutator, the Lie bracket of L with itself, is strictly contained inside an L. Okay, good. So now this means that we can choose a codimension 1 subspace I. Okay, we can choose something. So L, this ideal here, is strictly contained inside an L. So there's space between the two of these. Why don't we just work with this? Why are we going to the trouble of looking at this new space? Well, we don't know. We're worried about the codimension 1. So we don't know that the dimension of this is 1 less than the dimension of L. If it is the 1 less than the dimension of L, then just let I equal to the bracket of L and L. Okay. If it's not, then just prove something larger. Sorry, let's choose something larger. Okay. And this is just as a vector space to start with. Okay, and it's clear we can do this. However, even though we've only chosen it as a vector space, we get that it's an ideal for free. Why? Because this guy is contained inside here. So remember, we check the ideal condition, the condition for I to be an ideal. Well, it would mean that L by I is contained inside an I. But L by I has to be contained inside an L by L, which is contained inside an I, therefore it has to be an ideal. Okay. So all that means is that all this means, or in total, is that we can choose a codimension 1 ideal containing L by L. So let us now follow an inductive argument as usual. Note first that 1 is trivially true for L is equal to 0. Okay, that's clear. You're asking about an element that's going to be common eigenvector for all of the elements of L. Well, if it's 0, then of course any element will be a common one with eigenvalue 0. So now let's assume that it holds, the inductive argument is going to go in the dimension of L. So starting from 0, that's good. Then we assume that it holds for all Lie algebras with dimension less than that of L. This means in particular that there'll be a common eigenvector, small v and v, for all y. Okay. Sorry, for all y in I. Because I is codimension 1, so it's strictly contained in L, it has dimension less than that of L, therefore we can apply the inductive hypothesis. Okay. Now, if we've got a common eigenvector for this y, that's the same thing as a linear function. So this is an idea. This is a elementary result that we use again and again. If you have a common eigenvector, then there will exist a linear functional, lambda, that goes from I into k, such that this is satisfied. This is basically your definition. What you have to do is then show that this definition of lambda is actually a linear map. But you see, this is more or less clear once you think about it for a second or two. Okay, so we've constructed, from our inductive hypothesis, we've constructed a lambda that goes from I to k. Now you'll see that what we have now is we've got I and lambda. We've got this pair that we used in the previous lemma to construct construct W, this L sub-representation. Okay, we defined it in terms of I and lambda, and then we proved that it was actually an L sub-representation. So we can apply it inside here. I mean, of course, that's what we're going to do in the next slide. So we take the space W, and it's defined just as it was defined before. Anything inside in our ideal, this ideal containing the Lie bracket of L and L, you're asking for all of those elements such that it acts according, it acts as it's written. But remember I said before, this space could be 0. Well, in this particular case we're looking at, it won't be, because of the inductive hypothesis. Okay, we showed that because it's by the inductive hypothesis, first part of Lie's theorem says that there will exist a common eigenvector for I. So the thing is non-zero. And by the previous lemma, as I was saying earlier on, it's necessarily an L submodule. Okay, this is where we're using the previous lemma that we went to all of the work to establish. Now, if we're given an X in L, such that X is not in I, okay, then the map, so we're now going to take this L representation that we have and work with it. So we choose an X in L, not in I. Such things exist, remember, because it's a strictly contained codimension 1 subspace. So we have such things exist. And now we look at the map X that goes from W to W. It does bring W to W because it's an L module, an L submodule. This has a non-zero eigenvector. And why is that? It's because we're assuming that K is algebraically closed. So in the previous lemma, we used the assumption that the field had characteristic 0. Now we're using the algebraically closed. We also need to use the assumption that it's got characteristic 0 because we invoked the previous lemma here. So we still need to assume that it's got characteristic 0, but in addition to this, we're assuming that it's algebraically closed. And then this is just, the thing here is this is just a single element. So you're basically asking that it's a non-zero eigenvector. You're asking that the characteristic polynomial of the matrix is going to split, which of course it does because we're assuming that K is algebraically closed. All right. And in fact, we now see that the definition of W implies that V is a common eigenvector of any element inside here, which is to say any element in L. Remember? So remember, every element of W is a common eigenvector of the I. Every single element. So that means in particular that this V, which is the common eigenvector, is the eigenvector of X. That, of course, would be an eigenvector for W. So this guy works. This V that we've now found does what it's supposed to do. And that's the first part finished. Okay, so a lot of information there, but you can come back and rewatch everything slowly at your own time. So let's move on to the next part. That 1 implies 2. So we now have 1 in our hand. So we'll use it to prove the second part. This is, remember, the proof of of Engel's theorem, this is how it worked as well. We have the first part and we use that to imply the second and the third part. Same thing here. So we're now going to use an inductive argument. As usual, no surprises there. Clearly, the result is going to hold when the dimension of V is equal to 1. Okay, so it's going to be inductive on the dimension of V now. Remember, sometimes we're inductive on the dimension of L, the Lie algebra. Sometimes we're going to be inductive on the dimension of the representation. Here, we're going to use an inductive argument on the dimension of the representation. Try to keep it clear in your head what the inductive hypothesis is labeling. So when it's 1, that's going to be clear. Maybe we can just go back for 1 second and look at Lie's theorem because you may have forgotten. Okay, so this is the first part, which is now proved. We've got this common eigenvector. And now we want to show that every matrix with respect to the representation, every matrix row of X is going to be upper triangular. There exists a basis such that the matrix is upper triangular. Okay, so that's why when it's got dimension 1, it's pretty clear. You've got a 1-by-1 matrix that every 1-by-1 matrix is upper triangular. Done. Okay, let's move on and assume that it holds for all representations of dimension less than n. So let V be the common eigenvector of L. Then remember this exists because we know the part 1 holds. Okay, so this is what we have. This is how we're using 1 to prove 2. Then what do? Well, we see that we've got a subspace because it's a common eigenvector of L. So this whenever we have a subrepresentation, as we saw in like the first lecture, I guess, you can always quotient out. You can quotient out by this, and then we're going to get, of course, a representation of dimension less. We're going to call this V prime. It's going to be dimension 1 less. Okay. Now, by the inductive hypothesis, this V prime will admit a basis, V2 prime all the way up to V prime n, with respect to which X is an upper triangular matrix. Now we can lift this basis to vectors contained in space that we quotiented. And then we see that V1, the vector that we got from part 1 of Lie's theorem, together with this V2 up to Vn, is actually a basis of V with respect to which row of X is upper triangle. So I've gone through this a little bit quickly. If you remember inside an Engel's theorem, when I was giving this on the blackboard, I explained it a little bit more carefully. But it's exactly the same argument here, that going from taking as an Engel's theorem, when you had a strictly upper triangular matrix and you were able to lift it up, it's exactly the same thing. So I'm not going to explain it again. Just go back and have a look at the previous lecture. Or just think about it in terms of, try to see what this means in terms of converting your operators into matrices and so on. Again, basically in your algebra, but it's good to sit down and be completely comfortable with what's actually going on here. Okay. And that's part 2, upper triangular matrices, existence of the basis in upper triangular matrices. And it's somehow what we're doing is we're basically inductively constructing using this special element, the special common eigenvector of all of the L's. We're using this to kind of sequentially construct this basis. And then with respect to this, by construction, the thing is actually going to be upper triangular. Now, next, let's take the basis that we constructed above, and let's define this nested sequence or chain of eigenspaces. So you start at the first guy, well, it's going to be 0. Then V1 is going to be the span, big V1 is going to be the span of small V1. Okay. That is to say, it's just the span of the common eigenvector of L. Then V2 is just going to be the span of V1 and V2. V3, the span of V1, 2, and 3, and so on and so on. And you see that each of these are actually sub-representations. Okay, because the matrix is upper triangular. because the matrix is upper triangular, it preserves all of these VKs. Just remember how matrix multiplication works, and that should be clear. Note, however, that because they're upper triangular and not strictly upper triangular, it doesn't map. It doesn't map like V2 into V1, or it doesn't map V3 into V2 and so on. It doesn't move you along the sequence. It stays because it's upper triangular, not strictly upper triangular, and that's the difference between this and Engel's theorem. However, what you can see by construction, just as happens in Engel's theorem, this doesn't change, is that the dimension of 1 quotiented by the dimension of the previous term is always going to be 1, because you're just adding in an extra dimension each time. That should be clear. And that's it. We've now proved Lee's theorem. We've now generalized Engel's theorem to Lee's theorem, moving from nilpotent to solvable. And these are very powerful results. Again, there's a lot. The proof is there's a lot there, but the only thing you're really using is linear algebra. So it's almost surprising that you can make such powerful statements about solvable and nilpotent Lie algebras, but that's how it works. Using, sorry, just linear algebra. Okay, so with that in hand, we can move on, and let's get an application. I said it's a powerful result, but let's see something that we can do with it. So let L be a Lie algebra over an algebraically closed field of characteristic 0. Remember, we used these two assumptions in the proof. We used the characteristic 0 in the proof of the lemma, the one where we constructed this L representation submodule, L sub-representation W. And we used the algebraically closed field in the proof of Lee's theorem, because we wanted that the characteristic equation of a certain matrix was going to split and hence have an eigenvalue, and for that we assumed algebraically closed. So if we want to apply Lee's theorem, we will always need to work over field. We will need to work over fields which are algebraically closed of characteristic 0 and of characteristic 0. And now, what does it say? Well, it says that a criteria for L to be solvable, L is solvable if and only if the first term in the central series of the derived series is nilpotent. Okay. So we discussed this before. When we first introduced solvable, we went in one direction. Okay. So what we really need to do is to go in the other direction. We'll remind ourselves of this at the end, but let's do the more difficult new direction first. So let's assume it's solvable, and let's prove that this commutator this Lie bracket is nilpotent. So consider the adjoint representation. Remember this, we were using the Lie bracket of L to actually represent L on itself. Now, it follows from Lee's theorem that we can find the basis of L such that all operators are upper triangular. Okay? Because this adjoint representation is an honest representation. For Lie algebra is solvable, then we know we have a basis. Even if the basis is a basis of the Lie algebra itself, it doesn't matter. There was no assumption on the representation. So the adjoint is a perfectly good representation. So Lee's theorem now says that we have this basis of, or the Lie algebra itself, such that all of these operators are upper triangular. Okay. Now, a basic fact from linear algebra, if you don't know this, you should think about it. It should become clear pretty quickly. That when you take the commutator bracket of any two upper triangular matrices, then the resulting matrix is strictly upper triangular. You take this, basically in both terms, in like A by B and B by A, the diagonal is going to be the same for both of them. So if you're subtracting these two matrices, you're subtracting one matrix from the other, then of course the two diagonals will cancel and you're left with 0. That's basically it. The diagonal of AB is going to be the same as the diagonal entries of AB will be the same as the diagonal entries of BA. Okay. Well, what does that mean? Well, that tells us that if we look at the adjoint of XY, it's a Lie algebra representation, so it's going to be equal to the adjoint of, oh, no, let me try that. Okay, you see what I'm trying to do. It's going to be equal to the adjoint of these two guys. And this is a strictly upper triangular matrix. Hence, for every z in L, the operator adjoint z is strictly upper triangular. And hence it's a nilpotent operator. But we knew from Engel's theorem that when these conditions hold, when we have the adjoint is strictly upper triangular, which is when the adjoint is a nilpotent operator for every element, then we know that that Lie algebra itself is actually nilpotent. Nilpotent is a Lie algebra. So applying Engel's theorem, we now see that L is nilpotent. So we're bringing both the Lie's theorem and Engel's theorem to the problem at the same time. So it's heavy machinery being applied. But once we have this heavy machinery, the argument is quite quick. And it tells us that whenever it's solvable, the Lie bracket of LL is nilpotent. Now going the other way, it's actually pretty easy. We discussed this before, but let's just remind ourselves. So conversely, if the bracket of L and L is a nilpotent Lie algebra, then it's solvable. Okay, but if it's solvable, that means that the sequence will terminate. Because remember, nilpotent applies solvable. It's a special case. In particular, we know that this bracket here, the sequence is going to vanish. And that means that L is actually solvable. So nothing really going on there except for the definition of solvable and nilpotent. So let's just go back a second and just look at this. So basically, it's another way of, we have many ways now of looking at the difference between solvable and nilpotent. And here's another one. It's basically saying that if you look at the derived series, it's asking that not the first part of the derived series, which is to say the Lie algebra itself is nilpotent, it's that the second one is. That's another way of looking at the difference between solvable and nilpotent. We sort of moved the nilpotency one step up in or one step down in the series. So we're going to look at it. Okay, and that's it. So we proved Lie's theorem and we've given an alternative characterization. So to summarize, what we did was we proved Lie's theorem and we gave a new characterization of solvability in terms of nilpotency. And that's it. Okay, so thank you. I will talk to you again next week.